Welcome back, Physics 30s, to our next lesson in Chapter 5. This is 5.5, and today we're going to be looking at the Compton's effect, Part 1. Okay, so one of the big ideas in this course is that in Chapter 4, we looked at light as a wave, but now in Chapter 5, we've seen evidence that light can behave as a particle. And these little tiny light particles we've been calling photons. Now, it is kind of weird that it can be both a particle and a wave, but our study of blackbody radiation and the photoelectric effect are pretty strong evidence that it does sometimes act like a particle. And the Compton's effect is even further evidence that we see light acting like a particle. So let's take a look at the Compton's effect. Okay, so remember in the first unit when we looked at colliding masses like this? This is what we expect particle things to do, to bounce off of each other and transfer energy. What we would expect for a wave is that it would bounce off of materials like we saw with mirrors, where the angle of incidence is equal to the angle of reflection. Or as we see with X-rays, it could pass right through a material, as this is used for medical imaging with X-rays. Yet when we test this and we send this light at this piece of metal, sometimes it bounces off at a weird angle like a ricochet and comes out actually at a different wavelength. That result is not what you would expect from a wave, but more close to what we'd expect from billiard balls or solid particles bouncing into each other and transferring energy. That bouncing off at an angle looks a lot like particles, and the change in wavelength is the transfer of energy. It changes wavelength and frequency because EMR can't slow down. It always travels at the speed of light. So when it gives up energy, it decreases its frequency and increases its wavelength. And since the energy of a photon is calculated with E is equal to HF, we now see that it's at a lower value. And this decrease in energy and scattering is the Compton's effect. So we're going to look at scenarios where photons crash into things like electrons, and we're going to treat these examples similar to how we saw particles crashing into each other in the first unit. However, there's going to be a couple differences, so let's take a look at some notes. So first, the Compton's effect is where EMR collides with a mass and transfers energy to that mass, changing its frequency, and then also scatters at these different angles, which we'll look at a little bit more in part 2. Now, like the collisions we saw in Unit A, momentum is going to be conserved in these collisions with a photon. And energy is also going to be conserved in these collisions, which is going to make it an elastic collision. A difference compared to Unit A, though, is that the photon is not going to change its speed. It's always going to travel at the speed of light, so when it gives up energy, it's going to change its frequency. Now, you may be wondering, but wait, the formula for momentum is P is equal to mass times velocity. I thought photons didn't have mass. You're right, they don't. But they have momentum? Yep, sure do. Well, how does that work? Because Einstein says it does. Oh, okay, fair enough. He's a smart guy. I trust what he says. That's a pretty good call. If you're ever in question about something in physics, it's a pretty good bet to agree with Einstein, especially when the concept relates to his most famous equation of E is equal to mc squared. What this equation means is that energy is equal to mass times the speed of light squared. And the speed of light is a constant, so it shows that mass and energy are kind of a related characteristic. And it leads to these weird conclusions that, like, if I take this spring and I compress it or squish it together, because it has more energy in it, it has more mass as I squish it further and further. Now, this would be a very small mass difference for a spring, but somewhere where this equation has a big impact on our lives is the sun. The sun is forming hydrogen into helium all the time. It's undergoing this fusion reaction. And the hydrogens it put together actually has more energy than the helium it produces. So what happens to the mass is it gets released as energy, and a lot of energy. As we can see in the formula, mass times the speed of light, which is a pretty high number, squared, making it a much bigger number, multiplied by mass gives you energy. So if only a small amount of mass makes a big amount of energy, how much mass could the sun really be losing? Well, it's actually a pretty big number. It loses 4 million tons every second. This is a huge amount of mass to lose, and it's losing it every single second. You'd think at this rate, our sun's going to be gone pretty soon. But that's the crazy thing. This change in mass in the sun, you won't even notice over your entire lifetime because the mass is so big, times 10 to the 31 kilograms, that you won't notice this difference over many years. So don't worry, the sun is not going to burn out anytime soon. Okay, so that might be interesting, but how does it relate to the Compton's effect? Well, our formula for momentum was P is equal to mv, or momentum is mass times velocity. A photon doesn't have mass, but it does have energy. So we can use Einstein's equation to use that energy to determine the momentum. So here's the two equations here. P is equal to mv and E is equal to mc squared. If I rearrange Einstein's equation for mass, I would get E divided by c squared is equal to mass. So now I'm going to take that mass energy equivalent and plug it in to mass for the momentum. That gives me P is equal to E over c squared times velocity. Now, because the velocity of a photon is the speed of light c, I can replace that with a c. Then I see c divided by c squared, and I cancel out the c. Now, this equation is useful. The momentum of a photon is its energy divided by the speed of light. But sometimes we don't know the energy, so to calculate the energy, we use E is equal to hf. So this formula of the momentum of a photon is equal to hf over c is going to be the formula we use most for calculating momentum in the Compton's effect. However, it is important to remember this is only the equation we're going to be using for massless particles. Don't try and use this for particles with mass. Okay, so now let's sum up what's going on. If we take a photon and collide it with another particle, like an electron in this case, they're coming in at 90 degrees, they collide, and they're going to bounce similar to two particles crashing together. The photon is going to give up energy and change its frequency and wavelength, and the electron would bounce off like this. I haven't made sure the angles are perfect or anything like that, but hopefully you get the idea that this looks kind of similar to collisions we saw in Unit A. And we have to remember that energy is going to be conserved. This is an elastic collision. How we would calculate the energy of an electron or a particle would be half mv squared, and for a photon would be hf. Then we would use the same formulas to get the final energy for the photon and the electron. However, I've put a little dash there, which means h times frequency prime. This is the new frequency. That's to indicate that it has changed. It's not the original one we had. It has changed in this collision. Now, also remember that momentum is going to be conserved as well. If we're calculating the momentum of the photon, we just saw hf over c, and we would use P is equal to mv for a particle. And again, we would use those formulas afterwards, knowing that the frequency will have changed for the photon after the collision. Now we're going to get to calculating angles and everything like that with this example. However, that's going to come a little bit later in part 2 of this video. For right now, we're just going to do calculations of momentum of a photon. So let's begin with this example. What is the momentum of a photon of blue light, which has a frequency of 400 nanometers? So I'll start with my equation. P is equal to hf over c. Now it didn't give us frequency, so we're going to have to convert the wavelength into frequency. Now, we did this a lot with other equations where we use the universal wave equation of c is equal to lambda f. Let's just rearrange this for frequency. I divide by a wavelength on both sides, and frequency is equal to c over lambda. I'm just going to plug that number in over here and write h is equal to c over lambda over c. And I've just plugged in that rearrangement. What we notice here is we can cancel out c. C on the top, c on the bottom, and I end up with actually a fairly simple equation with h over wavelength is equal to the momentum of our photon. So we use Planck's constant, the one in joules, 6.63 times 10 to the negative 34 joule seconds, divided by our wavelength of 400 times 10 to the negative 9 meters. And I'm getting an answer of 1.66 times 10 to the negative 27. And that's going to be in kilograms meters per second or Newton seconds, because we were using that joules in Planck's constant. And that's what I'd recommend you use. Now that is a pretty small amount of momentum, but this also isn't that high energy of photon. It's still light, it's still blue light. If we got into X-rays and gamma rays, the momentum would increase as we would decrease this wavelength. Then we get more and more energy. Let's try one more where it says, what is the momentum of a photon with 8 electron volts of energy? So if we start with our equation, P is equal to hf over c. This may seem like, well, I don't know where energy necessarily comes in here. However, remember that to get this formula, we had E on the top here, and we know E is equal to hf. So before we got this as a final equation, we had P was equal to energy over c. So now I'm going to use that value for energy. I just have to convert it into joules. So I'm going to take 8 electron volts times 1.6 times 10 to the negative 19. That's our conversion to joules. And divide by C, 3.0 times 10 to the 8 meters per second. Plug that in the calculator, and I get 4.27, or 6 repeating, so we'll round that to 7, times 10 to the negative 27. Again, not very much momentum, kilogram meters per second, or Newton seconds. That's again because it's a really small energy photon. As we increase, we would get more and more momentum. Okay, so that's it for part 1 of the Compton's effect. In the next video, we'll be looking at these collisions in more detail and looking at angles. But I hope that helps you to understand what the Compton's effect is. Thank you so much for watching, and I will see you in the next video.